Today we're going to talk about emissions. This is better, right? We're going to talk about emissions of greenhouse gases, mostly CO2. That's just because of time. And we're going to talk about scenarios of emissions, and we're going to talk about the technical options for emission reduction. So that is the plan for today. I don't think I'll need all the time, so I'm also going to, at the end, talk about geoengineering, which is another way of solving the climate problem. This is where we are in the sequence. Last week we did the science of climate change. Next week we're going to do the costs of greenhouse gas emission reduction. Today it's just technical options. You're looking here at the entire sequence. At the moment, strikes have been announced for week 4 and week 6. As I said, I can drop lecture 12. I'm not quite sure that I can drop lecture 4. We actually did a lot of that last term. So this would not be so much the theory of how to regulate the environment, but would rather be how the environment is regulated with regard to climate. I am reluctant to drop it.
Are you striking?
I haven't decided yet. I really haven't decided yet. There's absolutely no movement from the university about anything, right? There's 2 strikes, right? One is about the pensions, where you can sort of put yourself in the position of the university that they simply do not have the money. Although they could be a little bit more assertive with regard to the behavior of our pension fund. Our pension fund is just losing money because they have idiot investors. That is a big part of the problem. And they have a very peculiar interpretation of the rules that are imposed by the central bank, right? The Bank of England. With regard to the other strike, equality and those sort of things, and workload, our demands are actually fairly low, that the university starts taking equality seriously. Just last week, a colleague handed in a resignation because of 10 years of misogyny, right? That's sort of bullshit that a university should go after, right? And that is one of our demands, right? That they start taking these things seriously. But they don't. They don't want to, right? They don't want to commit to taking equality and diversity and inclusion seriously. So there is definitely the university is at fault there. So I haven't decided what I'm going to do. Looking at the schedule, 1 week of strike would be, I think, the most I can afford without seriously hurting you guys, which is, of course, the last thing on my mind, right? But yeah, for now, we just pretend that this is what we're going to do. Okay, last week I showed you this particular graph, which has how did the radiative balance change over the last 250 years, 270 years even. And I put this up to show you the complexity of the climate problem, but also because you see that there's so many agents there. It's not just CO2, it's not just methane, it's not just nitrous oxide, but we have the halocarbons, we have ozone and the precursors of ozone, we have the aerosols and so on and so forth. We have land use change. Go ahead.
What's a halocarbon?
Halocarbon is Now you're testing my chemistry. CFCs and HCFCs. So these are industrial gases that are used as solvents and propellants and those sort of things. So CFCs are used in fridges as coolants. They're used in spray cans for paint and hairspray, not that you would use any, right? And so on and so forth. Deodorant.
For example, did the hole in Australia, in the ozone?
In the ozone layer, not the hole in Australia. Yes. And then the HFCs or the HCFCs are the gases that replace them. Good thing about HFCs is that they do not destroy ozone. Bad thing about HFCs is that they're stronger greenhouse gases than the CFCs. And HFCs are essentially used for the same purposes as CFCs. So these are industrial gases. They're also there's no fire extinguisher in this room. They're also used in fire extinguishers. Maybe there's one in the back that we can't see. And so on and so forth. And they're in your fridge and so on. But they're also used to make semiconductors to resolve parts of the silicon. Dissolve part of the silicon, not resolve. So that immediately implies, this is the complexity, that immediately implies that if you want to fully understand the climate problem and solutions to it, then you need to do something about all these gases, right? So it's not just CO2. Of course, because of time, I'm going to talk mostly about CO2. And the justification is that CO2 is the biggest contributor. And if we then look at this graph, it is global emissions in the year 2010 and their contribution to total greenhouse gas emissions in the year 2010. What you see is that CO2 covers roughly 75% of the problem, right? Methane adds around 17%, nitrous oxide around 7%, and then those halocarbons that we just talked about. SF6 is not a halocarbon, but it's usually grouped within there. Is only 2 or 3% of the problem, right? So that justifies focusing on CO2, even though it's not the whole problem. This graph also shows you where does this CO2 come from. Now 36% of the total problem is from the generation of electricity and heat production. Around 15% is in transport, around 15% is in manufacturing, and then 7% globally comes mostly from heating homes, as well as, no, this is heating homes because air conditioning is of course here. There's a little bit of cooking, but that doesn't take a lot of energy. It's from heating homes where the 7%, most of the 7% comes from. Right, so this is roughly where the problem or the origin of the problem lies. So let's look a little bit further, deeper into this. So carbon dioxide is by far the most important anthropogenic greenhouse gas, right? And most of the CO2 comes from the combustion of fossil fuels. So what you do is you take a hydrocarbon, say a block of wood, and or coal or gas or oil for that matter, what you do when you want heat out of that is that you add a flame to it, right? You add energy to the coal or the wood. And you add energy because you want to break the chemical bond between the carbon atoms and the hydrogen atoms that make up a carbohydrate, right? You add energy, you break the chemical bonds, then you add oxygen, you blow on the fire, and when you add oxygen, those carbon atoms and those hydrogen atoms oxidize, hydrogen atoms to H2O, water vapor. That's the smoke that you see come off of the fire. And the carbon atoms to CO2, carbon dioxide. And when those new chemical bonds are formed between carbon and oxygen and between hydrogen and oxygen, that is when energy is released. And that is why burning wood gives off energy, gives off warmth, right? The same is true when you burn coal, when you burn oil, when you burn gas. The implication of this is that the only way to get energy out of a carbohydrate is to oxidize the stuff. That is to form CO2. It's from the formation of CO2 that the energy is generated, right? So as economists, we look at CO2 as an externality, where there's an unintended, uncompensated impacts on a third party of what we're doing. But from a physical perspective, it is intrinsic. You can't get the energy out of the fossil fuel without making CO2, because it's in the making of the CO2 that you get the energy. This sets climate change apart from a problem such as acid rain. Acid rain also is caused by the burning of fossil fuels, but it is because in most fossil fuels there's also little bits of sulfur. And when you burn coal with a little bit of sulfur in, you form SO2. And SO2 is the cause of acid rain, the sulfur. But from a chemical perspective, that is a nuisance that actually reduces the efficiency of your power plant. You actually don't want that sulfur in there. But for CO2, we actually do want, from a physical, chemical perspective, we actually do want the CO2 coming out of our power plants. So that makes this a problem that is hard to solve, right? Because you can't get energy out of fossil fuels without making CO2. Now, fossil fuels are not all created equal. If you burn peat, it is very young fossil plant material. Peat is typically only 1,000 years old or so. You emit a lot of CO2 per unit of energy generated. Much more than if you burn coal, which is much older plant material, typically million years old, or petrol or gas, you emit even less CO2. And you see the numbers here. Peat, it's 117 tons of CO2 per terajoule of energy, whereas gas is only 57. Of course, you do not need to understand the unit tons of CO2 per terajoule, but you understand the difference between 117 and 57, right? Go ahead.
Is diesel quite a CO2 fuel?
We'll get back to diesel in week 8. Diesel has lower CO2 emissions per mile driven than petrol. And that is not so much the composition of the fuel, but it's the efficiency of the engine. Diesel engines are simply more energy efficient, generate less waste heat than Otto engines that burn petrol.
But what about, because was it about the 2008 Volkswagen that was like released, and then there was a mass recall because the engine was just like spewing out way more emissions than was regulated. And then there was the whole thing about lots of other German manufacturers.
The problem with diesel engines is that they generate more soot, more particles than petrol engines. That actually cools the climate because it reflects sunlight directly and it acts as cloud condensation nuclei. But another problem with soot is that it's very bad for your health, because these are very fine particles that cause all sorts of respiratory problems and also cause cognitive problems. So we don't want the soot from at all. Now, the reason that Volkswagen first and later others got into hot water about this is because they had made this claim that they had developed a clean diesel engine that did not emit so many particulates. It turned out, and as a result, because we now had an engine that emitted less CO2 and did not have the air pollution problems that came with diesel engines, a lot of countries sort of put very heavy emphasis on promoting diesel engines for about 10 years, and then it was discovered that these tests that Volkswagen and Renault and a lot of other companies had put forward to show that these diesel engines were clean, all those tests were actually falsified, and they were not clean at all. Still haven't quite gotten to the bottom of this scandal, because people suspect that it wasn't just the companies who were doing this, but there was active involvement of certain government agencies to let them cover up these faulty tests. And that then goes back to the heart of the Merkel government, right? Now that there's been a change in power in Germany, we may actually get to the bottom of it. Although it may be too embarrassing for the entire. It was mostly the Germans as well as the French government, right? It was French and German companies that did this. Right. Where were we? So different fossil fuels have different CO2 emission intensities, which immediately gives you an option to reduce emissions, right? If you switch from one of the lower emission intensities to one of the higher, rather the other way around, you actually reduce emissions. And what you're looking at is 3 pictures of the US power sector. I mean, just ignore the middle one. In the left, you're looking at what fuel was used to generate electricity. Here it is measured in how much electricity was generated. Here it is measured how much energy was put in. So the difference between the two is conversion efficiency. And what you see is that over this 20-year period, natural gas has replaced coal. And the reason for this is the discovery of shale gas, or rather the discovery of how to get shale gas out of the ground in a profitable way. So this is vertical drilling and fracking and those sort of things. So that is what happens, right? You see that all other fuels are basically constant. So this includes the renewables, right? You see that if you compare this number to this number, total fossil fuel input was roughly the same over the 20-year period. Then these are the associated CO2 emissions, and what you see is a very sharp drop, right, in emissions. And this is because natural gas only emits 2/3 as much CO2 as coal. So this is a definite option to reduce greenhouse gas emissions, right? The problem with the discovery of shale in the US is that they have a lot of coal mines. So gas became cheaper. Nobody wanted to buy coal anymore. So there was a surplus of coal. So coal became cheaper as well, right? So what we've seen in other parts of the world, including in Europe, is, because in Europe we don't do shale, right, that much, at all, for that matter. In Europe you actually saw a little bit of the opposite effect going on, because coal got so much cheaper as a result of the shale gas revolution in the United States. So this is definitely an option for greenhouse gas emission reduction. Now, don't hold your breath here, because of this picture and the next one. What you're looking at here is the world energy supply, and some of the names that I gave this picture are a bit peculiar. So we start in 1820, we end 10 years ago. This is where we derived our energy from. At the bottom we're looking at muscle power. It's called food here, but this is human energy, cycling and pulling plows and that sort of stuff. Burning of fuel wood, animal power, so this is draft animal, horses, oxen, those sort of things. Coal, oil, gas, electricity is hydro, and later on wind and solar, and then nuclear power. And this is perhaps better seen as a share of the total. What you see is that yes, if you look at a 50-year period or a 100-year period, you see fairly dramatic changes, right? And you also see that those transitions are actually fairly slow. It's not that we can completely change the energy sector in 10 years' time. We have never ever done anything like that in the past. And the reason for that is that the energy sector is fairly big, right? It serves 8 billion people by now, 7.5 billion people by now. The other reason is that a lot of these things rely on long-lived capital. Cars take 10, 20 years on the road, right, before you replace it with a new car. Buildings last for decades, if not centuries. Power plants, gas-fired power plants, they could have a lifetime of around 25 years. Coal-fired power plants have a lifetime of 60 to 80 years, right? So transitions in the energy sector are very slow. Oil platforms are supposed to last 40, 50 years, right? So yes, there's a lot of invested capital, and therefore transitions definitely do happen and have happened in the past, but they're always slow, right? So let's continue the story, and for some reason now everything is on this slide already. So the combustion of CO2 is the major source of greenhouse gases, but there's other sources of greenhouse gases as well. One is land use change. So I talked about wood, right? Trees are made of carbohydrates. The same is true for grassland, but it's much smaller, right? So much less CO2 is stored in pasture land than in a forest. So if you convert, as we have done, forests into pasture lands and then into arable land, you lose a lot of CO2, right? Typically how this is done is that the forest is burned, right? That's the fastest way of clearing land. And then a lot of CO2 is released into the atmosphere. And this is still going on in South Asia, Southeast Asia, in large parts of Africa, and of course in South America. There's still deforestation going on at a fairly rapid scale. In Europe and North America, it's now the other way around. We have become so good at agriculture that we don't need all this agricultural land, and we are gradually letting the forest grow back in Europe and North America, right? And then we take up CO2. The third and smallest source of carbon dioxide is the production of cement. And cement is essentially limestone that is heated at a very high temperature, and if it's heated enough, then the CO2, the carbon in the lime disappears. It's oxidated to CO2, and that chemical transformation then turns limestone into cement. And again, this is intrinsic to the product, to the process. The only way to make cement out of lime is to get rid of the carbon in the lime. And that means, and the cheapest, the simplest way of getting rid of that excess carbon is to oxidize it to CO2, right? It's responsible for around 3% of CO2 emissions. The solution here is, of course, to switch to alternative building materials. There's been substantial progress in there. Some people are switching back to to lime, which is actually also a good building material, not as good as cement, but it's a decent building material. And we're now also looking at these fabricated woods, and they're building skyscrapers out of wood nowadays, and that would be one solution there. Of course, if that wood comes from trees that have been replaced, right? You cut down the tree and then you plant a new tree, then you're actually taking up CO2 when the new tree grows. But if the old tree is not burned, but instead processed and stuck into a building where it will last for another 100 or 200 years, then of course no CO2 is released from that tree, right? And you actually take up CO2 from the atmosphere. So that is where CO2 comes from, and that is roughly what you can do about it and how complicated it is, right? Because it's one thing to build a skyscraper in Genoa out of wood, as they indeed have done. It's another thing to convince the Chinese that all their new buildings should be made out of fabricated wood rather than out of cement, right? That is a completely different story. The second most important greenhouse gas is methane, CH4, which comes out of four sources, two processes really. The first is the production of meat and milk. So if you look, what does a cow do? A cow eats grass and produces milk, right? So you can see this as a chemical transformation of grass into milk. But if you compare the chemical composition of the two, then you would see that there's more hydrogen in grass than there is in milk. Both are carbohydrates. So somehow along the way the cow needs to get rid of the excess hydrogen. And that happens in the stomach of the cow. Hydrogen is dangerous. If you have hydrogen floating around in an environment with a lot of oxygen, then it goes to OH, an oxygen radical. And the problem with OH is that it destroys everything. It reacts with anything and everything, and leads to a lot of chemical deterioration of the environment. Fortunately for cows, there's very little oxygen in their stomachs. The second thing that hydrogen can do as an atom is that it can go to H2, hydrogen gas. And that is the stuff that lifts up zeppelins, right? It is also not something you want in your stomach, right? So what the ancestors of cattle have done a long time ago is that they formed a symbiotic relationship with methanogenic bacteria. And what those bacteria in their stomach do is that they sacrifice one carbon atom, and that is what we want, right, for the milk, in order to get rid of 4 hydrogen atoms and form CH4, methane, and that is then burped out by the cattle, right? So that is where the CH4 comes from. And again, it's chemically necessary to do this. You need to get rid of the excess hydrogen. There's no way you can make meat or milk without methane. Now, there's a couple of solutions to this. Go ahead.
I'm sorry, so are you saying that cows don't produce methane naturally? It's something that humans are interfering with?
Well, it's not something that a cow does, it's something that the bacteria in their gut do, even. And that's a natural process that I think has been around for hundreds of millions of years. So it's not just cows that do it, but all ruminants, right? Camels and everything do the same thing, the same chemical biological process is there. So how would you get rid of this? Well, there is another group of animals that forms the same ecological function, right? They eat grass and transform it into meat and milk, and that is kangaroos, right? and they produce acetate rather than methane, which is less efficient. So one way of solving this is to switch from cow's meat to kangaroo meat, right? That would reduce CO2 emissions. Now, I'm a vegetarian. I've never tried it, but my brother-in-law has, and he says it tastes awful. So this may not be an acceptable solution, but tastes differ, right? Another solution would be to move away from cow meat to chickens, are more efficient, or move to a meat-free diet. What farmers are promoting at the moment are additives to the feed, particularly seaweed, that actually reduces methane emissions. Cannot take it away fully, but it reduces methane emissions, which is a solution for intensive farms in Ireland and Wales. It is not a solution for extensive cattle farming in Brazil, right? Because A, it's far away from the sea, so getting the seaweed there is hard, but also these animals essentially roam free rather than being penned into a small field, right? So it's just not an option there. Second big source of methane emissions is paddy rice. So that is wet rice, rice that is grown underwater. And the process is fairly similar to what happens in a cow's stomach. So rice plants have leaves, those leaves drop to the ground. If plant material degrades in an oxygen-rich environment, then it goes to CH4, right? If plant material degrades in an oxygen-poor environment, underwater, then it goes, no. If it's in an oxygen-rich environment, then it goes to CO2. In an oxygen-poor environment, there's no O2, it goes to CH4. So if the plant material, those leaves, drop underwater, it goes to methane and then bubbles up under the water. And if you've walked in swamps, you would sort of see the swamp gas coming out in some places, right? What can you do here, right? The issue with paddy rice is that this is the most productive agriculture that we know in terms of how many calories can you get out of an acre of land. That is why all over Asia people grow rice in water, because it's just the most productive way of feeding people, and population densities are very, very high in those parts of the world. There's very little you can do, right? You could put a cap over the fields and capture the gas, but that would be fairly expensive, right? To put a ceiling, put a roof over all rice fields, and most of this is grown by fairly poor farmers, right? So they would not have the capital. So you can eat less rice, but you need to feed the people, right? So this is a fairly intractable problem. There has been some good news or bad news, depending on which side you're on. They're genetically modifying rice, putting in genes of barley into the rice, which has the advantage that the plant will send more of its nutrients to seed formation rather than leaf formation. The advantage of this is that as a farmer, you don't care about the leaves, you care about the seeds, right? That is what the rice is. So it's good for the farmer. It's also good for methane emissions. But of course, for European sensitivities, genetically modified rice may not be what we want, right? But that seems to be, or at least in my mind, is the best solution for getting rid of at least some of the methane from paddy rice. Another big source of methane, a very similar process, comes from waste. That is, we throw away a lot of food stuff. If that food rots in an oxygen-rich environment, it goes to CO2. If the food rots in an oxygen-poor environment, that is in a landfill, it goes to CH4, right? actually putting a roof over landfill and capturing the CH4 is actually a viable technology because landfills aren't that big compared to dairy rice, and they typically happen in richer countries as well as in poorer countries. So that is the solution there, but an expensive one. The fourth source of methane is, I've been calling it methane, CH4. CH4 is actually one of those strange things. It has multiple names, and natural gas is methane, is CH4, right? So if it is a nuisance, we call it methane, and if it's useful, we call it natural gas, and we burn it to heat our homes. If you're transporting natural gas through a pipeline, and that pipeline is not fully sealed, some of the methane gets out and into the atmosphere, right? So that is a source of methane emissions. Also, if you're mining coal, there's often bits of methane that comes out as well. If you know the history of miners, those explosions in coal mines are because of methane exploding and burning. And if it doesn't explode, then it just leaks into the atmosphere, right? And the same is true for if you mine, if you drill for oil, then you typically also find methane there, and that is why you see all those flames around oil fields. That is the methane that is being burned. So the solution there is, instead of burning the natural gas, is to stick it in a pipeline and use it. Simple solution there, right? And of course fixing the leaks in pipelines of natural gas transport. All of this comes at a cost, right? I mean, the oil companies are not stupid. They're not burning the gas because they do not know it is useful, right? Most oil companies also sell gas. It's just that the transport costs are too high compared to the sale revenue. So that is where methane comes from. And you see, again, there are some intractable problems here, right? It's not easy to solve this. Nitrous oxide comes mostly from agriculture. So in order to make our plants grow, our crops grow faster, we put on fertilizers. Those fertilizers contain nitrogen. Most farmers are risk averse. It's much better to apply too much fertilizer than to risk a bad harvest. So too much fertilizer is applied, there's too much nitrogen in the soil, then through chemical transformations in the soil, that nitrogen goes to nitrous oxide, N2O, and gets into the atmosphere and stays in the atmosphere for 300 years or longer, and is a fairly potent greenhouse gas, right? And the solution there is use less fertilizer, right? Go ahead.
Is the emissions of greenhouse gases in the sort of milk alternatives, like, how does it scale up against each other and milk itself? And just from like an emissions perspective, not going into the welfare aspects.
You mean almond milk and oat milk, those sort of things?
Yeah, soy and all that stuff. If you know it, anyway.
I don't, but I should. Are you familiar with Our World in Data? Okay. Google Our World in Data, which is a big data operation run out of Oxford University. And they have recently done a comparison of the greenhouse gas emissions for milk substitutes. And I only know that they have done it. I don't know what they found. My recollection is that it's a bit better, but not a lot better, and it all depends on what is your substitute. And soy milk, for instance, is not that good because...
Don't you have to import water and bees?
Not for soy. Soy isn't good because most soy is grown on what used to be rainforest. But almond milk comes out a lot better for CO2, but then almond milk comes out bad for pesticides and for water use. So I don't think it's a simple cut there. But there's definitely people who have done those calculations. I just don't have them on the top of my head. We talked about the industrial gases, right? The CFCs, the HFCs, the SF6, which come out of very specialized applications, mostly in industry. So, that's where CO2 comes from. The next question is, how does it evolve over time? And I'm gonna do a little bit of that, and then we're gonna have a break. This is CO2 from the combustion of fossil fuels worldwide from 1970 to 2014. I do realize that I can actually push this to 2018 or 2019, but haven't done so. So that is the black line that you see here. We normalize everything to 1. So there's an index number in 1970, and then you see that by the year 2014, CO2 emissions have more than doubled, grown by 125%. And the question is, why, right? What drives these emissions? And one way of trying to understand the past is to use the so-called Kaya identity. And that is given here, and I realize also that the notation is slightly different than in the book, where it says that emissions E equal the number of people, P, times per capita income, Y over P, times the energy intensity of the economy, X over Y, where X is energy use, times the carbon intensity of the energy sector, E over X. Now this is true, right? Because P cancels against P, Y against Y, and X against X. So this equation says that emissions equal emissions. So it is true, right? It is also useful because you know now where do these emissions come from. If I see a change in my emissions, I can actually decompose it into these 4 components. And that is what the rest of the graph does. The red dots are population growth over the same period, again indexed to 1 in 1970. And what you see is that population grew by some 80% over this period. CO2 went up by 125%. So the implication is that we now emit more per capita than we did 50 years ago, right? But the difference is actually not that big, right? So that is the first thing you see. The blue line is income per capita. Again, over the same period, again 1970 is 1. And what you see is that income per capita went up by some 110% on average for the world as a whole over this period. Again, CO2 emissions rose faster. But total economic growth is, of course, the blue line times the red line, right? So if population doubled and if income doubled, roughly, then the size of the economy quadrupled, right, over the same period. Emissions went up only by 125% rather than by more than 200%. So the emission intensity of the economy must have fallen over this period, right? And that you see in the, I'm going to call this purple and green line. In purple, we're looking at the energy intensity, X over Y. How did emissions change? No, how much energy did we use per pound value added? And what you see is that over this period, it almost halved. That is the economic output that we got per unit of energy input almost doubled over this period. Right? You get twice as much value out of a unit of energy than we used to get 50 years ago. Actually, if you think of it, quite impressive. And then the fourth component is the carbon intensity. How much CO2 did we produce per unit of energy used? And that has hardly budged, right? You see that it actually went from a climate perspective the wrong way, right? As we burn more and more coal, then we had the oil crisis and that sort of stuff, and then it actually came down. We started switching to gas in this period, but then we had the rise of China first and India later, who burned a lot of coal, and it went the wrong way again. So for all the talk about renewables and stuff, it actually did not change much from a global perspective over this 50-year period. Go ahead.
So I might have missed it, but so if that energy intensity, what sort of energies is that, or is it just everything but carbon?
This is all energy.
Oh, okay.
So, well, I say all energy. I showed you this graph, right? So it's the fuel wood. No, this is traditional biomass. It's not included because all of this is subsistence. So it is everything but the bottom three. So the coal, oil, gas, the renewables, the nuclear, all added together, and then all added together, of course, in an energy unit, right? In the terajoules or something like that. So that's the energy input.
Do you know the like the rate of change at the moment for energy intensity? Like what's the trajectory? How fast is it changing?
This is 1.5% per year. Has been 1.5% per year for a long time and hasn't changed much. It goes up and down a little bit between 1.4 and 1.6%, but it's roughly 1.5% per year for as long as we have measured this thing.
Why do you think it's quite constant? Because I would sort of assume that it could potentially like act as a proxy for just, I don't know, technological improvement. So then I would sort of guess that in sort of big jumps of technological improvement there might be like a big surge and then it might then slow down. But obviously it's not that. So it's sort of a bit.
No, I mean, as you see, it is not.
Yeah, but
It is not always the same number, right?
Yeah.
But it's always around that number. The reason that it develops slowly is the same as why transitions in the energy supply are so slow. A lot of it is driven by long-lived capital. It is true that if you get a new car, it is more energy efficient than your old car. And for you as an individual consumer, when you switch from a 12-year-old car to a 1-year-old car or a new car, it is a big jump. But of course for the economy as a whole, that is not the case, right? It is just every year new cars on the road are slightly more fuel efficient than old cars. The same is true for laptops, the same is true for mobile phones, the same is true for buildings. Every time we build a new house, it is better than the average fuel efficiency or insulation of older houses. But of course we do not replace the building stock every year, right? We tear down a few old buildings and we build slightly more new ones. And the same is true for machinery and so on and so forth. So if you look at individual products and you compare their energy performance of a new product to one that is 10, 15, 20 years old, you see a big difference. But if you look at the average across the economy, and definitely if you look at the average across the world for all economies, things gradually improve. And of course, that is true for individual products, right? But at the same time, we are coming up with ever new things that use energy, right? And that then pushes the trajectory in the opposite direction.
So why is energy intensity consistently going down, but then carbon's not, because surely carbon is
Yeah, why is it going down?
composed in well,
Yeah.
a part of energy intensity as well.
No, the two are separate.
Oh,
This is the carbon intensity of the energy sector. This is
okay.
the energy intensity of the economy. The reason that it's going down is because energy is a cost.
No, I get that. I was just
Yeah.
confused because I thought we might have
Yeah.
some.
No, there's no overlap. This is a simple separation. Okay, let's continue. I need to speed up a little bit. I decided what bits I'm going to cut and race through. So last week I showed you a variant of this graph. How much warmer will it get during your lifetime? Where the sort of the central lines are sort of the average across models and the median, and then the areas that you see is the uncertainty between the climate models. But then the different colors denote different scenarios of emissions. Scenarios are not implausible, internally consistent ways in which the future might unfold. And what you see is that the scenario uncertainty, how much emissions there will be in the future, is actually more important than the uncertainty about the climate models. Right? That is what drives the difference between the upper end and the lower end of the projections. The chi identity actually also allows us to not just decompose past emissions, but also allows us to project future emissions. So if we want to know what are emissions in the year 2100, what we need to do is know how many people there will be in the year 2100, how rich they will be, how much energy they will use relative to the size of the economy, and what sort of energy they would use, that is how much CO2 they will emit per unit of energy. Right? And because climate is such a long-term problem, we actually need to do this for at least a century, but probably more. Right? And not just for CO2, but then also for methane, which is mostly related to the agricultural sector. So we also need to project what people will eat and what percentage will be vegetarian, and so on and so forth. Right? So you see that this is a major forecasting problem, right? And therefore people in this field prefer to talk about scenarios rather than about forecasts, because nobody in their right mind would try and forecast this, right, more than a few years into the future, and even those would be rather peculiar. So let's look at the standard set of scenarios that are used in this literature. I say standard because it's such a big job that this has essentially been monopolized by a particular consortium of researchers. And I've split those projections according to the chi identity. So here we're looking at projections of the number of people in the future. I see a fair bit of uncertainty there, right? The lowest projection says that the world population will return to about 7 billion by the year 2100. The highest projection says it's 13 billion. That's a difference of 6 billion people, right? Most of this is driven by different assumptions about the speed of the decline of fertility in poorer countries. So the difference between the upper line yellow and the lower line in purple is essentially it's 6 billion here, but 5 billion of those are African children or children born in Africa, right? So that is a major uncertainty. These are the projections of how rich we would be or will be in the future for the world average. This is an interesting picture. The most pessimistic scenario says that the average income in the world will rise from the current around $7,000 per person per year to over $20,000 per person per year, and that's the most pessimistic scenario. And it would be a good scenario, right? 21,000 is the income of people in Portugal now. And if that were the living standard, the average living standard across the world in 100 years, in 80 years' time, that would solve a lot of problems, right? Go ahead.
Wouldn't it be really hard to even like forecast the purchasing power and like potential inflation in that future?
Absolutely. I'm not talking about the credibility of this at all, right? Actually, I was going to talk about credibility. The most optimistic scenario has the average world income at 135,000. The richest country in Europe at the moment is Luxembourg, with an income of $105,000 per person per year. And this projection is that by the end of the century, the average person on the planet will be richer than the average person in Luxembourg is now, right? And of course, if the average goes across the world goes to 140, then there will be a large chunk of people who are millionaires, right? And a large chunk of people who are billionaires and trillionaires. It's very difficult to imagine a future like this. Then again, if you go back 100 years in time and you would describe how we live now and how wealthy we are compared to your grandparents and your great-grandparents, they would not believe you, right? So maybe this is true, maybe this is not true. The interesting bit relating to Max's question, the reason that there's no disaster scenario here, or no scenario even in which income stabilize, is because this is a product of the United Nations. And the people who put this forward simply did not dare contradict the often very rosy projections of their own governments and say, yeah, you say you're going to grow, but I don't believe you. So that is why everything is going up. Energy intensity is projected here. Again, 5 alternative scenarios. Here we have the observations, and you see, saw it in the previous graph, a steady decline in the energy intensity, steady improvement of energy efficiency. The projection is that this will continue into the future, essentially because energy is a cost. If you can make the same product but it uses less energy, then people will buy your stuff. Right? And the projection is that this will continue at different rates, none of which is historically implausible into the future. Although in the very low scenarios we may be sort of bumping into the laws of physics, right? Because still, in order to move things, you need to put in energy, and you have resistance and waste that is cannot be avoided. But the projections don't look entirely crazy. The projections of carbon intensity have the widest spread, right? The most pessimistic models actually see it increase, and other models see a very rapid decrease. You also see that people actually disagree about the past, reasons I won't get into. But most scenarios come down, right? This is, I think, a bit optimistic because we've seen that it's basically stable, but once the scenarios kicks in, it comes down. But then there's some important exceptions here. And these exceptions, of course, where the carbon intensity goes up rather than down, lead to very high emissions. And because emissions are high, it's good for your climate model, because you have a very clear signal, very good experiment, right? You give your model a big kick and see what happens. It's much more interesting than giving your model a small push and see what happens, right? Nothing much is the answer. So climatologists like high emissions, right? Because it really tests their model. Environmentalists also like high scenarios, high emission scenarios, because then you can tell stories of alarm and doom and catastrophe about the future. So most of the literature, and definitely most of the press coverage, is actually on the high end of the emissions rather than in the middle, including scenarios where the carbon intensity stays constant or even increases. And the assumptions that people make in these models is that when we run out of oil and gas, which we will before your life is over, oil before your life is over, gas maybe before my life is over, when we run out of conventional oil and gas, what are we going to do then? These models assume that we're going to go back to coal, and that we're going to gasify coal and we're going to liquefy coal. We know how to do that, and use that to run our economies. If you look at the price of coal relative to the price of wind power and solar power, now we won't, right? You would be absolutely crazy to invest in new coal at the moment, thermal coal. But these models assume that for some reason wind and solar will become very expensive in the future, and coal will stay very cheap into the future, even though we are also running out of accessible coal reserves. In some of these scenarios, people are mining coal in Antarctica. Right? There's a lot of coal in Antarctica, there's no doubt about that. And going to Antarctica to mine for coal and then ship it all the way to Europe, it seems a bit far-fetched. It seems a very expensive way of doing things when you can just put up wind turbines in Europe, right? But that is what these models assume, perhaps less incredibly so. But these are the scenarios that we have, and this is what drives most of the literature. Now, the more interesting question is, so we have our emissions, now we want to get rid of them, right? How would you do that? And again, the Kaya identity comes to our rescue. So the Kaya identity that I just gave you is that emissions equal number of people times per capita income times the energy intensity of the economy times the carbon intensity of the energy sector. Now, if this is true, then it's still true if you take the log on both sides of the equation. If E is E, then log E is log E, right? We just transformed both sides of the equation, be the same thing. It's still true if then on both sides of the equation, that if you take a log, of course this multiplication becomes a summation, right? That is what logs do. It is still true if then on both sides of the equation you take the first partial derivative to time, right? So d log e dt is d log p dt, y, x, and e, right? I took something that is true and I just transformed it and it's still true, right? Now this, I think, well, what is this? What do I do with the first partial derivative of a log to time? Well, first partial derivative d log e dt, chain rule. First partial derivative of e to anything is 1 over, the log to log of anything to anything is 1 over e, right? Chain rule dE dt, right? So this thing can also be written as the change in E. This is just a change in notation. And then we have the change in emissions over emissions. This is the proportional growth rate, right? This is the growth rate of emissions. So that's why we took the log, not just to get rid of the awkward multiplication and replace it with summation, but also because of this rule. So what we have is that the growth rate of emissions equals growth rate of the population plus the growth rate of per capita income plus the growth rate of the energy intensity of the economy plus the growth rate of the carbon intensity of the energy sector. Right? This follows from the Kaya identity and some calculus. So what we want for emission reduction is this thing has to go negative, right? That is what emission reduction is. The emissions do not grow, but shrink. That is, d log E dt should be negative. And we have 4 basic options to do this, right? We can reduce the growth rate of the population, we can reduce the growth rate of the economy or per capita income, we can save energy, and we can switch to different energy sources. The Gaia identity tells you there are 4 basic options to reduce your emissions. Is that so? Well, not really. Reducing population growth, I mean, we have crazy politicians in this country, but they do not dare mess with the number of children that you guys plan to have, right? That is political suicide to suggest, to say I'm going to interfere in the number of people you have. So that is not really an option that is on the table. There are, of course, countries that have active population policies, like Sudan, for instance, for a long time actively killing, Syria for a long time actively killing people in their own country, government of Zimbabwe, of course, actively driving people out of their country. Colombia is another example. Yes, there are governments that do this, but perhaps they are not the nicest. China, for a very long time, during climate negotiations, has argued that its one-child policy is its major contribution to international climate policy. Complete nonsense. The one-child policy was introduced for different reasons, and at times that we did not really worry about climate change. And now that China is beginning to worry about climate change, they're abandoning their one-child policy because they're worried about pensions and so on and so forth. So it's a complete bogus argument, but it's one that has been used by the Chinese government over and over again. The second thing that, so yes, this is an option, but perhaps not one that is politically feasible. Reducing economic growth, making people poorer, is very effective. Very effective. This is the per capita income in blue, and CO2 emissions in red in the former Soviet Union, and then in the countries of the former Soviet Union, including Lithuania. And what you see is that from 1960 to 1990, two basically grew hand in hand. Growth rate was roughly the same. Then the Berlin Wall came down, the Soviet Union collapsed into 15 independent countries, and you saw the economy just being wiped out, and emissions just fell with it, right? So this is a very effective policy for reducing emissions. Actually what happened after is that the economy started growing, but because it was completely different economy, emissions did not pick up nearly as fast. So this is a very effective policy. It is not something that you want to stand on for re-election or election. Like, I'm going to tank the economy to reduce emissions. No, that won't work. There's, of course, it can happen by accident. The Japanese economy hasn't grown that much. The European economy has been sluggish for a while. And of course, because of Brexit, the UK economy is now taking a very big hit. But of course, the politicians there who promoted Brexit do anything in their power to deny that even the economy took a big hit, right? We've seen that over and over again. This is not something that you stand on and say, look, you guys, I'm going to make you poorer, vote for me, right? It's not really an option. That means that we have basically two options only, right? But it's a bit worse than that. We want this one to go negative. We don't want to touch this, and we want this one to be positive. We want people to be richer. Which means that if emission growth goes negative, emissions are falling, then these two do not just have to be working towards reducing emissions, but actually have to overcome population growth and economic growth, right? They actually have to be bigger. These two together have to be bigger than these two together in order for emissions to fall, right? So that's an important thing to keep in mind. Now, how can we save energy? How can we improve the energy efficiency of of our production and consumption? There's two basic options there. One is technological change, and we already talked a little bit about that. Newer products tend to be more energy efficient than the older products that they replace. And the reason for that is very simple. Energy is a cost. So if you can save on your energy cost, then your product becomes more attractive, or you have more money for other things, right? So if you can heat your home by replacing your heating system by one that is more efficient, that is, it gives more heat per unit of energy that you put in, and essentially you keep the heat the same and you use less energy, that means that your energy bill comes down, right? So that is attractive for you as a consumer. Also, if you're a producer of heating systems and you offer a model that has the exact same specifications as the competitor, but you use less energy per unit of heat produced, then of course people will buy your product rather than the product of your competitor, right? So also from the perspective of the companies that make and sell and design and develop these things, saving on energy is simply good business, right? So that is why you saw energy intensity come down over the last 50 years. Bill Nordhaus has a paper out where he pushes the efficiency of lighting back to Babylonian times, and we've seen the same thing there for the last, what is it? Now you're testing my Bible knowledge. For the last 3,000 years or so. Don't hold me on the most part of Babylonia actually. So this is just, it has happened, right? And there's no reason to assume that it will not continue to happen in the future. There is an important caveat though, and that is, yes, it makes good economic sense to save on energy use to make your product more energy efficient. The question is, of course, what is this technological progress used for? This is perhaps the starkest example. What we're looking at here is the fuel economy of new cars on the road in the United States. And it's not energy efficiency, it's the other way around, so it's miles per gallon. And what you see is that indeed from 75 to 82 is steadily improved, right? You filled up your tank, but your car drove further with the same tank of gasoline. But then from 1980 to the year 2010, it basically stabilized. No fuel efficiency improvement whatsoever in the car fleet, the new sold cars in the United States. The reason for this is in this particular graph, these two particular graphs. So this is the weight of cars on the US road. What you see in this period, 1980 to 2010, cars got a lot heavier. I don't know whether you guys have been to the United States, but you have no doubt seen SUVs on English roads, and they are big. They're not. You go to the US, you can see really big cars, right? Really, really, really big cars. So that is one thing that happened. And because of that, because you have an ever larger car, an ever heavier car, you need an ever more powerful engine to actually make the thing go, right? And this is the average horsepower of those engines over the same period. So this graph is actually quite remarkable. you have ever more weights and ever more volume being pulled around without actually using more energy. So all the improvements in fuel efficiency did not go towards using less energy, but it went towards pulling larger weights around, right? So this is actually a remarkable feat of engineering, but it was directed towards comfort and safety and status and those sort of things rather than reducing emissions, right? And the same is true for if you replace your heating system, right? Yes, you can use this to use less energy for the same temperature, but of course you can also use it to raise the temperature in your house from 16 degrees on average to 18 degrees on average, right? While using the same amount of energy, right? So it's not necessarily that this technological progress, what is going on, and no doubt, is directed towards saving emissions. There's further complications here, and those are the behavioral issues. So if you ask an engineer, he or she will tell you that about 30% of our energy serves no particular purpose. So this is people boiling a full kettle to make a single cup of tea, right? You heat all that water and then you let it cool down again. What's the point? People leaving the light on in the bathroom. You're no longer in the bathroom, so why is the light on, right? A lot of energy is wasted. So that would suggest that you can get rid of 30% of energy and therefore roughly 30% of emissions without any effort, right? But the problem there is that habits are hard to change. It may actually be unpleasant to change habits. So the government occasionally puts ad on the telly and say you should save energy, you should use less energy, right? Most people just ignore this. I guess a lot of you live in shared accommodation. You may live with somebody who goes around giving out to you that you left the light on in the bathroom again and you should really turn it off and think about the polar bear and that sort of stuff. You may even be that sort of person, right? But that can create social tension, right? And may actually not help. And if you try and do it on my kids, they actually do the opposite of what you say, right? So it doesn't help at all. So these things are, yes, they're habits, and changing habits is always hard. There's also structural problems here, and economists call these principal agent, where principal is with the PAL, not the PLE. And a principal agent problem is, for instance, this classroom. So I am the agent. As a lecturer, I am responsible for turning off the lights and the beamer and everything after class, right? That is my role, that is my responsibility. I do not pay for the electricity. The Vice Chancellor does. If we save on electricity, then the Vice Chancellor will not raise my income, will not give me more research money. The Vice Chancellor will do whatever the Vice Chancellor does with extra money, right? Probably hire some assistant to help him tie his laces or something. Not somebody who does anything useful for me, for sure. So why would I, right? So I am the agent, I control the resource, but I do not pay the bills, so I have absolutely no incentive whatsoever to use those resources efficiently. Now that is the smallest problem, but the same is true, for instance, in the housing sector. Most of you live in rented accommodation. You pay the energy bill, but you are not allowed to change the structural features of your apartment. The landlord or the landlady does that. So if you want to put in double or triple glazing, or you want to put in wall insulation, you're not allowed to do that. That's the job of the landlord. But the landlord would be costly to do so. But the transmission of information in the rental sector is such that a landlord cannot demand a higher rent for a better insulated apartment. Only very weakly, right? So there we have a principle. You pay the energy bill. The principle, the landlord is expected to invest in energy efficiency, wall insulation, and so on and so forth, but cannot recoup that investment and therefore has no incentive to do it. Right? This is a structural problem. You see it throughout the economy in all sorts of things. This is very hard to change, right? Because this has to do with property rights, it has to do with contracts, and so on and so forth. If you want to incentivize me to turn out the lights at the end of a lecture, essentially that would require that I pay for the electricity, right? So when I walk into a lecture hall, I need to swipe my identity card, and from that point on, this electricity bill goes to me, right? And then I swipe it when I leave it, so the problem is then for somebody else. That would completely change my labor contract, right? It would also require quite an investment into IT, and university is so good at IT that it will probably fail for the first 20 years or so, right? So those things are hard. Similarly, in the rental sector, you essentially need to change rental contracts. So what they are doing at the moment is putting these energy labels up everywhere, and that has been going on for a while. And what we see is that indeed this information, your apartment is rated C or B or G, that indeed affects the rent that you pay, but it is not a one-on-one. That is, the difference in energy bills is not fully compensated by this extra information that is given. So it's simply, these things are hard to solve, right? You can say, well, 30% of energy is wasted, let's go for the 30%. But it's actually, these are hard problems to solve. Not in theory, but in practice they're hard to solve. Another thing that you can do is convince people to use less energy. Put on a sweater rather than heat your home. Go on holiday in Devon rather than fly to Thailand. Right? And those sort of messages will appeal to a small minority of people, but won't appeal to the vast majority, right? To sacrifice part of their comfort for the benefit of the climate, right? Which is a fairly abstract thing for most people. So that leaves us with using different sources of energy. So I talked about some of these things already. I talked about switching from coal to gas already. You can of course switch away from fossil fuels altogether to nuclear, hydro, wind, solar, biomass. There is no physical problem here. If you just look at the amount of solar energy that we receive every year and compare it to the total demand of energy imaginable, then we can supply the world's energy needs many times over with renewables. There's no physical problem. There's also no technical problem, right? Wind power, hydropower, nuclear power, solar power, biomass power are all proven technologies. So there's no technical or physical problem here. The problems are of a different nature. I'm going to skip this graph. I don't know why I have all three together. Nuclear power and hydropower are the older technologies. Hydropower is actually the oldest way of generating electricity. for the first couple of months that there was electricity in England, it was all hydropower. It was 100% renewable. That is something that lasted 6 months, and then they started burning coal. But we started with hydro. Lasted a little bit longer in the United States, where the first 1.5 years or so of electricity generation were all hydropower. And then they switched to coal. Nuclear power is of course younger. This is post-World War II. They are carbon-free, basically. Not entirely. Hydro, you need a lot of cement, right? So there's some emissions there. Hydro, you have large water bodies, so you have some methane emissions. But by and large, these are carbon-free sources of electricity. And you can say, well, we should just expand that and expand that rapidly to solve our CO2 emissions. There's two problems with that. One is that people don't like nuclear power because they're afraid of accidents, they're afraid of the waste. Neither of them is actually a problem. They used to be problems, but they have technical solutions. It's just that it hasn't penetrated into the masses' minds that these are real solutions and that new built nuclear power plants are inherently safe. They cannot do a Chernobyl, they cannot explode. You cannot have a 3 Mile Island any longer, right? And not with the new designs, but people don't realize that. And also, the waste problem is basically solved by sticking it in glass and essentially neutralizing the radiation. But people are not convinced, and this actually drives up costs, and drives up costs considerably. A large part of the costs of nuclear power nowadays is the insurance that you need and all the extra safety measures that you need, and that drives up the cost of nuclear and just makes it more expensive. Hydropower is also difficult in that sense. What you need for a big dam is a big lake. That is, you need to displace lots of people. You need to ruin nature, destroy heritage and those sort of things. And people are just not keen on an expansion of hydropower in North America. They're actually actively taking hydropower dams down in order to restore nature. So a large expansion of these two is just not really feasible. With nuclear, you also have the problem of proliferation. If you're smart enough to operate and run a nuclear power plant, you're also smart enough to make at least a dirty bomb, right? So the only way to make a real dent in emissions, global emissions of CO2, is not to build a power plant somewhere in England, right? Or to build more power plants in China. But if you want to make a real dent in emissions, you need to build lots of nuclear power plants in Pakistan and the Central African Republic and places like that, right? Where A, you would not have the qualified engineers to run them safely, and B, you have either governments or other organizations, terrorist organizations, who would like to get their hands on nuclear material and do things with it that are not peaceful, right? So, no. Technically, yes. Politically, socially, perhaps not. What you can do is use wind power. These slides are old. When I wrote these slides 10 years ago, wind was expensive and solar was expensive relative to fossil fuels. That is no longer the case. One was enough. So what you're looking at in blue is the development of the cost given in dollars per megawatt hour of generating wind power onshore and offshore. And you see that that has steadily declined over the last decade or so. And forget about the tracking. photovoltaics have declined faster, right? From around $350 per megawatt hour to around 50 in 10 years time, right? A factor 7 in costs. Now, as I said, I've been lecturing about this for a long time. Nobody saw this coming, right? Anybody who now claims he saw this coming is just a liar. Nobody saw this coming 10 years ago. Now, this $50 per megawatt hour is not a unit that means much to you, right? Coal-fired power is about 40, gas-fired power is around 60. This is competitive, right? In ever larger parts of the world, solar power is the cheapest way of making electricity, period. Wind in increasing parts of the world is cheaper than gas-fired and coal-fired power nowadays. And offshore wind is getting there. Offshore wind is actually coming down much more rapidly than the cost of onshore wind. The progress in photovoltaics is mostly better materials. These are breakthroughs in material science, essentially, that spill over into the photovoltaic market. And this is still the old stuff, right? We haven't got to the perovskites yet. That is the solar cells that are flexible, that you can just put in your coat or in your bag, rather than in a hard fixed panel on your roof, right? Those things aren't even on the market yet, but you can expect this to continue to go down. With wind power, it is, because these are essentially rotor blades, right? This is essentially what was in propeller planes that you see in movies of World War I and World War II, right? That's essentially the technology that they're using here. And the reason that the costs are coming down is because of economies of scale in production, mostly, is why the costs are coming down. It's not so much technological progress in the things themselves, although as materials getting better and control technology is getting better, but it's mostly on the production side that things are improving. And these things are getting ever bigger. And that means that you actually has two advantages. A, it's cheaper per megawatt hour. Second, you have momentum. So I was born in 1969, right? But the first oil crisis is something that is in my living memory, right? 1973, and after that, sort of like these first wind turbines went up, and crazy little things that went really, 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 really fast, which makes you dizzy when you look at it. But also the problem with these things is that if the wind stops, the propeller stops. So you have a very variable input into your electricity system, which is not what you want. Whereas these very big turbines that we have now have so much internal momentum that small variations in wind speed do not affect in any material way the amount of electricity you generate. You have a much steadier input of electricity, which means that it's actually much cheaper to run, because you don't have to regulate frequency and have more backup and so on and so forth. Which is not to say that wind and solar are not without its problems, right? Wind is visually intrusive. People hate wind turbines. Solar panels are full of nasty chemicals, so there's a waste problem. And of course, the sun doesn't shine at night. You don't have solar power. If the wind doesn't blow, you don't have wind power, so you require storage. That's the second thing, revolution that is going on. Cost of batteries have come crashing down, right? Batteries used to be terribly expensive, but they are not anymore, right? And again, this is driven by progress in material science. There's absolutely no reason to say, well, this trend will stop. So you require storage. Also, the best winds and the best sun is where there's no people, right? So you also need to transport this, which costs a lot. Wind and solar make electricity, which is good for your laptop and your mobile phone. It's good for the lights, not so good for transport. And yes, electric cars are coming, but electric cars are still good as a second car if you live in the city. They're not good as a family car, and they're not good if you drive irregular distances or long distances. So what you can do there is use bioenergy. Essentially, what people have been doing is take maize or take seeds, rapeseed for instance, and turn it into a liquid fuel or into a gaseous fuel even. This stuff is expensive. It's typically impure, so if it burns you produce much more particulates and those sort of things, bad for health. Deer don't like rapeseed because if they eat it they die, and so on and so forth. There's all sorts of issues with this. The most important issue is just fundamental. This is very oil seeds essentially turned into oil by pressing it, right? The problem there is you have recent plant material that is no good, and then you need to collect it, you need to dry it, you need to transport it, you need to press it, you need to process the whole thing, and then you have something useful. Whereas if you take oil, and essentially Mother Nature has done all this compacting and drying and conversion for you, right? So essentially what you do when you make biodiesel from rapeseed is you're doing all those things that Mother Nature has done for you for free over the last couple of million years and stuck it into an oil reservoir. So this is just more expensive. There's no two ways around it. Sorry. So that is the first generation of biomass. There is a second generation of biomass, and that is essentially that whole conversion process from the field to the car, the tank of your car, is streamlined with better and more modern techniques. Oil presses go back to Roman times or earlier, right? We now can do better than the Romans. Problem with both first and second generation biomass is that it directly competes with food. If you use corn to make ethanol, as they do in the United States, that means that corn is not used to make tortillas, right? And that drives up the price of corn. And also that corn is not used to feed pigs, and that drives up the price of pork, right? So directly competes with food. However, there is also a third generation that people are talking about, and that is probably best illustrated with this particular graph. So all these, well, most of these plants are familiar to you, right? Cauliflower and broccoli and kale, you know about kohlrabi, you may have heard about Brussels sprouts, it's been Christmas, right, and carrots. You've seen all these things and you've probably eaten most of them. This is all the same plant. You would not realize, right, that broccoli is the same as Brussels sprouts, but it is. Or I pointed to cauliflower. And they all descend from the mustard plant. You probably also had mustard, right? And what has happened is that over the last 2,000-3,000 years, people through selective breeding have turned this particular mustard plant into this range of vegetables. So quite an enormous diversity, but also an enormous improvement in efficiency, right? That this little plant which does not have much nutritional value is turned into plants that have great nutritional value. This was done over a period of 2,000-3,000 years through selective breeding. That same period our energy crops are basically still the same as they were when the ancient Romans, the ancient Greeks were around. So what is happening in labs around the world at the moment is that people are taking energy crops and transforming them into better energy crops by improving the oil content of the seed and so on and so forth. And you can see the same revolution going on here. But of course now we have genetic engineering. We understand all these processes much better than our ancestors did. So you can expect a lot of progress here. And perhaps the most promising ones are when we're manipulating algae. Because the good thing about algae is that they grow out at sea, so they're not competing with food production. And we never really touch them. There's now algae that essentially have been manipulated. You put them in a vat of water, you come back 2 weeks later, and there's a film of biodiesel at the top. Your vat of water, you scoop it up, you stick it in your car, and you drive away. Those sort of things are now emerging in the labs around the world. They have not found any commercial application yet, but give it 10 years and those things will be there. And then we're probably, with bioenergy, we're probably going to follow one of these two tracks. 1 minute. That the costs will be coming down and you can expect large-scale commercial application. The implication of this is, of course, then yes, it will also be cheap and easy to decarbonize the transport sector, which at the moment looks like a bit of a nightmare still.